Okay, I can see that 5 people have joined, so we will not waste any more time. It's 10:35 a.m. already, and let us start the class. So those who have joined the class may give their attendance in the chat box. I repeat, those who have joined the class may give their attendance in the chat box. Just give me a minute so that I can present my screen. Can anyone please respond whether my slides are visible or not?
Yes, sir, it is visible.
Okay, thank you. So, good morning to all of you. Let us continue from where we have left behind. If you remember, we were solving the problems related to direct stiffness method, and in the last few classes we have derived the stiffness global stiffness matrix for a particular problem by direct stiffness method. Today what we will do is we will solve some numerical problems related to that direct stiffness method. So let us take the first problem of today's class, and that problem is, yes, this one. Let us read the problem. The problem tells you that using the direct stiffness method, formulate the global stiffness matrix and determine the displacement at nodes of the spring system shown in the figure. Consider spring constant K1 equal to 40 Newton per millimeter, K2 is 50 Newton per millimeter, K3 is 80 Newton per millimeter, and point load acting at the third and the fourth nodal point, that is P3 is 60 Newton and P4 is 50 Newton. Also calculate the reaction forces. So what is given to us? In the given problem, it is very much clear from the diagram that the given problem consists of three elements. This is element number 1, which is connected between node 1 and node 3. Element number 1 connected between node 1 and node 3. This is your element number 2. Somebody is joining. Wait. Yes. So this is my element number 2, which is connected between node 2 and node 3. Element number 2 connected between node 2 and node 3, and this is my element number 3 connected between node 3 and node 4. Element number 3 connected between node 3 and node 4. So it is very much clear from the diagram that the given problem consists of total 3 elements. And how many nodes are present? Total 4 nodes are present. And if in altogether there are 4 nodes present in this entire problem, then I know that the global stiffness matrix for the entire problem will be nothing but a 4 cross 4 matrix. That means it will have 4 rows as well as 4 columns. I know that size of the global stiffness matrix depend upon the number of node present in the problem. In the given problem, in altogether 4 nodes are present. So the size of the matrix, global stiffness matrix will be 4 cross 4 matrix. Is it clear to all of you? Any doubt so far? Hello.
No, sir. No, sir.
Okay, and from the diagram, it is also clear that node 3 is a common node. Node 3 is a common node connecting element 1, element 2, and element 4. And from the given problem, it is also clear that if I assume that U is the linear displacement of each and every node, fine. Then from the given diagram, it is very much clear that displacement U1 will be 0 as well as displacement of the second node will be equal to 0. Why? Because first and the second node are the fixed nodal point. So displacement will be 0. Remaining nodes, that is third and the fourth node, we will have some displacement. Let that displacement is denoted by at node 3 displacement is U3, at node 4 displacement is U4. I am assuming that displacement U3 is along this direction and displacement at node 4 is along this is along negative x direction. If at last in the last my answer of U3 and U4 comes out to be negative, that means I have taken the wrong direction of U3 and U4. Direction will be in opposite nature. Is it clear to all of you so far? Any doubt?
No, sir.
Okay. So the boundary conditions which I get from the problem is U1 and U2 is equal to 0. Fine. And one more boundary condition, that is the fourth boundary condition that is given is P3, that is load, point load acting at nodal point 3 is how much? It is 60 Newton, and point load acting at node point 4 is how much? It is 50 Newton. Since it is acting along negative x direction, so let us assume that P3 is equal to minus 60 kilonewton and P4 is equal to minus 50 Newton. Fine. Okay. So let us solve the problem now. Since I need to find out what I need to formulate the global stiffness matrix for the entire problem. Before that, what I will do, I will find out the local stiffness matrix for each and every element. That is for element 1, what is the stiffness matrix? For element 2, what is the stiffness matrix? For element 3, what will be the stiffness matrix? And then we will assemble all the three stiffness matrix for each of the individual element to get the global stiffness matrix. So let us find out individually the local stiffness matrix for each and every element. For element number 1, what will be my local element stiffness matrix? So this is my element number 1. I can see very clearly that element number 1 is connected between node 1 and node 3. And since this node 1 is fixed end, so let us assume that at node 1 force acting on the node, first node is what? F1 along negative x direction. Fine. If at last my answer of F1 is comes out to be negative, that means I have taken the wrong direction. Direction will be along positive x axis. Fine. So this is my F1. This is my F1 and displacement of node 1 is U1 in this direction, and at node 3 already force P3 is acting, which is equal to F3 in negative x direction. So this is your force F3 and displacement of the node 3 is u3 along negative x direction. Fine. Then I know that what will be the size of the local stiffness matrix. The size of the local stiffness matrix will be equal to the total number of nodes present in the element. In the element number 1, there are total 2 nodes present. One is node number 1 and another one is node number 3. So the size of the local stiffness matrix will be a 2 cross 2 matrix. 2 rows, 2 columns. The first row will be node 1, second row will be node 3. Similarly, first column will be node 1 and second column will be node 3. In between, what will come? This stiffness will come. That is K1 minus K1 minus K1 K1. This we have derived in the last class, that stiffness matrix for an element is given by K minus K minus K K. Since here in element number 1 stiffness is K1, so it will be K1 minus K1 minus K1 K1. In the given problem, value of K1 is given to you, that is 40 Newton per millimeter. Just evaluate those values. Then the resulting matrix becomes 40 minus 40 minus 40 40 Newton per millimeter. That is the let you call this matrix to be matrix A. Is it clear so far? Any doubt? Any doubt so far till matrix A? Hello.
No, sir. No, sir.
Okay. Similarly, I have to write down the element stiffness matrix for second and third element. If I consider second element, I can see that second element is connected between node 2 and node 3. So let us assume that the nodal force of node 2 is F2 along this direction and nodal displacement is U2 along negative x direction. Similarly, at node 3, nodal displacement is U3 along negative x direction and nodal force is how much? Nodal force is nothing but P3, which is equal to F3 and its magnitude is 60 Newton. I am assuming it to be negative since the force is acting along negative x direction. Fine. Now for this element, I have to construct the local stiffness matrix. Again, I know that what will be the size of the local stiffness matrix? It will be of 2 cross 2 matrix because element 2 comprises of only 2 nodes, that is node 2 and node 3. So you can see that the stiffness matrix for the second element is given by, it is a 2 cross 2 matrix. The first row is nothing but the second node. The second row is nothing but the third node. Similarly, the first column is your second node. The third column is your third node. And these values are what? This is nothing but the stiffness values. That will be K2 minus K2 minus K2 K2. In the problem, value of K2 is given to you. So just evaluate those values and the final matrix becomes 50 minus 50 minus 50 50 Newton per millimeter, which is acting between node 2 and node 3 along row wise and in column wise node 2 and node 3. Let it be represented by B. This is matrix B for second element. Any doubt so far?
No, sir.
Okay. Similarly, for third element, I can see from the diagram that the third element is connected between node 3 and node 4. So this is my third element which is connected between node 3 and node 4. So let us assume that the linear displacement of third node is u3 along negative x direction. Linear displacement of node 4 is u4 along negative x direction. Nodal point forces acting at node 3 is F3, which is equal to P3 in negative x direction, that is minus 60 Newton, and at node force, nodal force present is F4, which is nothing but P4 and is equal to minus 50 Newton acting in negative x direction. Since element 3 is present, or element 3 comprises of node 3 and node 4, so the local stiffness matrix for element 3 again will be a 2 cross 2 matrix. The first row indicates node 3, first row indicates node 3, second row indicates node 4, first column indicates node 3, second column indicates node 4. In between, the inside the matrix, what is this value? This value is nothing but the stiffness value. It will be K3 minus K3 minus K3 K3, and since in the problem value of K3 is given to you, you can see that value of K3 is how much? 80 Newton per millimeter. So just substitute the value of K3. I will get the resulting matrix as 80 minus 80 minus 80 80 Newton per millimeter. Let it be matrix C, present in between node 3 and node 4. Is it clear to all of you? This matrix A, B and C for element 1, 2 and 3. Any doubt so far?
Yes, sir.
Okay. So now in order to get this global stiffness matrix, what I need to do? I need to assemble matrix A for first element, matrix B for second element, and matrix C for third element. If I will assemble these three matrices, I will get a global stiffness matrix. And what will be the size of global stiffness matrix? The size of global stiffness matrix will be the total number of node present in the entire problem. I can see that in this problem, total number of node present is how much? It is 4 nodes: node 1, node 2, node 3 and node 4. Total 4 nodes are present. So the size of the global stiffness matrix will be a 4 cross 4 matrix. That means there will be 4 rows as well as 4 columns. Is it clear to all of you?
Yes, sir. Yes, sir.
Okay. So let us formulate that global stiffness matrix. So this is your 4 cross 4 global stiffness matrix, in which the first row will be what? Nodal point 1, second row is nodal point 2, third row is third nodal point, fourth row is fourth nodal point. Similarly, first column is first nodal point, second column is second nodal point, third column is third nodal point, and fourth column is fourth nodal point. In between value inside the, that means this is what? This is a 4 cross 4 matrix. In between, I have to assign the values. How I will assign? You have to assemble it. That means this value is what? This value is first row and first column. So from matrix A, B and C, I have to find out 1 cross 1. So let us find out from matrix A. I can see that the value of, I can see that the, yes, this is 1 cross 1, value is 40. In equation number B, there is no 1 cross 1. In equation number C, there is no 1 cross 1. So the resulting value of 1 cross 1 is how much? It is 40. Now let us find out this 1 cross 2, that means this value. So let us find out from the matrix A, B and C. So in the first matrix, 1 comma 2 is not present. Second matrix, 1 comma 2 not present. Third matrix, 1 comma 2 not present. So it will be how much? This value is 0. Similarly, let us find out 1 cross 3. That is this coefficient will be what? first row and third column. So let us find out. In first matrix, first row and third column is minus 40. Second matrix, there is no first row and third column. In third matrix, there is no first row and third column. So it will be minus 40. Likewise, you have to complete this entire global stiffness matrix. Is it clear to all of you? Any doubts
Yes,
so
sir.
far? Hello?
Sir, clear.
Okay. So let us find out, say, this particular value. Let us find out this particular value. This will be how much? This value will be the third row and third column. So let us find out. That is the third row and third column from first matrix. That is matrix A is how much? It is 40. From matrix B, the third row and third column is how much? It is 50. And from matrix C, the third row and third column is how much? It is 80. So this overall assembled value of this third row and third column will be how much? It will be this 40 plus 50 plus 80. See, 40 plus 50 plus 80. Likewise, I have to do. But somewhere, say if this 50, if this 3 cross 3 from matrix B, if this 50 is minus, then my resulting answer would be 40 minus 50 plus 80. That will be this value. Is it clear to all of you? Any doubts
Yes,
so
sir.
far? Hello?
Clear, sir.
Fine. So
Yes.
likewise, you will complete this assembled global stiffness matrix, and after completing, the final assembled stiffness matrix is this matrix. That is this particular matrix, in which each and every value is almost same except this value. This value will be how much? It is 50 plus 40, that is 90 plus 80, that is 170 Newton per millimeter. So this is the first part of the answer which you have to find out. That is, you have to compute the global stiffness matrix. Is it clear to all of you? Any doubt so far?
Clear,
Hello?
sir. No.
Okay. Next, what I need to find out, in the problem, it has been told to you that you need to find out the displacement of the nodes. That means U1, U2, U3, U4, out of which two displacement only you know, that u1 and u2, value of u1 and u2 is how much? It is 0, since it is fixed, and only I need to find out the displacement u3 and u4. For that, what I will do, you have already did in the last problem, that first you need to find out the First, you need to find out the governing algebraic equation of the problem. We know that the governing algebraic equation for the problem is what? It is nothing but F is equal to K into displacement, that is restoring force. We are not taking the minus sign, so F is equal to K into U. If I write this equation in matrix form, I can write it as matrix vector F is equal to global stiffness matrix K into nodal displacement vector U. Fine. This is what? This is the governing algebraic equation of the entire problem. Fine. Since we can see that in the given problem, total 4 nodes are present. So I will get total 4 different equations, 4 different algebraic equations. That means this value of u, this value of u is how much? It is nothing but a column matrix. It is nothing but a column matrix of the order 1 cross that is of the order 4 cross 1, that means 4 rows and 1 column. First row will be nothing but first node, displacement is u1. Second row is nothing but second node, displacement u2. Third row is nothing but third node, displacement u3. Fourth row is nothing but fourth node, displacement u4. Similarly, this nodal force vector is again a 4 cross 1 matrix. It is again a 4 cross 1 matrix. That is first 4 rows and 1 column. The first row is what? First row is nothing but the nodal force present at the first node, that is say F1, which I have to find out, because in the question it has been told to you that you need to find out the reaction forces also. So if I draw the FBD of this problem, then I can see that reaction force is F1, which this wall will give to this node 1, and reaction force is F2, which this wall will give to the node 2. So this is your F1. Similarly, along node 2, nodal force present at node 2 is F2. At node 3, nodal force present is F3, which is given in the problem that F3 is nothing but P3, and it is how much? It is 60 Newton. I am taking it negative because it is acting in negative x direction. So this F3, that is this F3 is negative minus 60. Similarly, F4 is given also. Similarly, F4 is also nothing but equal to P4, acting at nodal point 4, and it is acting along negative x direction. So the value of P4, again I am taking it as negative, that is minus 50 Newton. That is minus 50 Newton. This will be the size of this nodal force vector, and what will be the size of global stiffness matrix? That is nothing but this matrix. So let us write in the matrix equation form. I can write that K into U is equal to F. K is nothing but this matrix, that is this particular matrix. This is your global stiffness matrix K into, this is your nodal force vector u1, u2, u3, u4 equal to, this is your nodal force vector f1, f2, f3, f4. This first represent node 1, this is node 2, node 3, node 4. Column 1 represent node 1, column 2 node 2, column 3 node 3, column 4 node 4. Inside the matrix, these values are nothing but these values, that is these values. So you will get this equation, this matrix equation you will get. Till this matrix equation, any doubt so far?
Yes, sir.
Okay, other people please respond whether any doubt is there or
No
not.
solution. No doubt.
Okay, fine. So next is what? Now, if I want to in this, so if you solve this matrix equation, you will get total 4 different equations. Fine. And from the diagram, it is very much clear that value of u1 is 0, value of u2 is 0, since node 1 and node 2 is fixed. So I can rewrite this equation as, this is your global stiffness matrix into this first u1 is 0, u2 is 0, u3 I need to find out, u4 I need to find out, which is equal to global force vector F1, F2, F3, F4. Value of F3 we know that is minus 60 Newton. Value of F4 we know that is minus 50 Newton. Now if you see, since u1 is 0, u2 is 0, then I think you have studied in mathematics one method. That method is called Gauss elimination method to solve the matrix equation. Gauss elimination method. Elimination, Gauss elimination method. This method tells you that if this u1 is 0, u2 is 0, and this first row represents u1, second row represent nodal point 2. Similarly, first column represent nodal point 1 and second column represent nodal point 2. Then you can eliminate completely the first row as well as you can eliminate the second row. Similarly, you can eliminate first column as well as you can eliminate second column. This is Gauss elimination method. If u1 is 0, u2 is 0, and I know that this first row represent what? This one represent what? This one represent first row of first nodal point. This one represent first column of first nodal point. This two represent second row of second nodal point. This second column represent second column of second nodal point, and if u1 and u2 is 0, you can eliminate the first row, second row and first column as well as second column. This is Gauss elimination method. So if I use this method, then my resulting equation will be in the form only I will be left with third row, fourth row, third column, fourth column. That means I will be left with this U3, U4, F3 and F4. So far it is clear to all of you. Any doubt?
Clear, sir.
Okay. Other people please respond whether it is any doubt is there or not.
No, sir.
Okay. So my resulting matrix becomes what? Now it is a 2 cross 2 matrix. Now this represent the third node. This is third row. This is fourth row. Similarly, this is third column, and this is my fourth column. That means this represents third nodal point, this represents fourth nodal point in terms of row, and in terms of column, this is third nodal point, this is fourth nodal point. Value is given, that is 170 minus 80 minus 80 80. See, 170 minus 80 80 80 into u3 u4, that is this will be what? This will be 2 cross 1, 2 cross 1 matrix. u3 u4 equal to 2 cross 1 nodal force vector minus 60 minus 50, because f3 is along negative x direction, value given is minus 60. f4 is along negative x direction, value given is minus 50. I am taking it to be negative since it is acting along negative x direction. So just multiply the matrix and you will get two equations. That is how we can multiply it. This row into this column will give you this equation. Similarly, this second row into this particular first column will give you this equation. Let us multiply it. 170 into u3 minus 80 into u4 equal to minus 60. Similarly, minus 80 into u3 plus 80 into u4 equal to minus 50. That is equation number 1 and equation number 2. If you solve, see, you are having two equations, you are having two unknowns, that is u3 and u4. If you solve these two equations, you will get the value of unknown displacements at nodal point 3 and 4, and that value is coming out to be u3 is minus 1.22 mm and u4 is minus 1.84 mm, and this minus sign indicates that I have taken the direction of displacement wrong. So my direction of displacement will be which direction? That means at node 3, displacement, direction of displacement will be in this direction. At node 4, direction of displacement will be in this direction. So this is the second part of this problem. That is, you need to find out the unknown displacement. u1 and u2 is already 0 from the boundary condition, and from this Gauss elimination method, I found out the unknown displacement value at node 3 and node 4, which is u3 is minus u3 is 1.22 mm and u4 is 1.84 mm. Is it clear to all of you? Any doubts so far?
No, sir.
Okay. Other people please respond whether any doubt is there or not.
Nice,
Clear, sir.
Okay, fine. So we got the value of u3 and u4. Similarly, next what I need to find out? I need to find out the reaction forces. That means I need to find out this value. That is, this F1 will be how much, and this F2 will be how much. How I can find out? Fine. If I take the first row, if I take the first row, that means if I multiply this first row with this first column, it will be equal to F1. So let us multiply, that is 40 into U1 plus 0 into U2 minus 40 into U3 plus 0 into U4 equal to F1. Since U1 is 0, so this 40 into U1, this is 0. 0 into U2 is 0. Minus 40 into U3. Since U3 is given in the problem, so I will take, so my resulting equation becomes minus 40 U3. This 0 into U4 is again 0. So this minus 40 U3 equal to F1. If I consider the first row, my equation will be minus 40 U3 equal to F1. So F1 is how much? Minus 40 into U3. U3 is how much? U3 is minus 1.22 mm. So F1 become minus 40 into minus of 1.22. So F1 is how much? It is 48.8 Newton. That means this reaction force F1 is how much? This reaction force F1 is 48.8 Newton. Similarly, I need to find out this F2. F2 is at nodal point 2, it is acting. So in this equation, in this particular equation, if I consider the second row, if I consider the second row, that means if I multiply this second row with this first column, I will get the value of F2. That is how much? 0 into U1, that is 0. 50 into U2, that is also 0 because U2 is 0. Minus 50 into U3 plus 0 into U4, which is also 0. That means minus 50 U3 equal to F2. So minus 50 U3 equal to F2. So F2 equal to minus 50 into U3. U3 is how much? Minus 1.22 mm. So F3 becomes, sorry, F2 becomes minus 50 into minus of 1.22 mm. So finally the F2 is coming out to be 61 Newton. So this F1 and F2 is what? These are the resulting reaction forces which this wall will give at nodal point 1 along negative x direction. Is it clear to all? Sorry, along positive x direction, because my F1 and F2 is coming out to be positive. So if you stretch this spring, the spring will give back the force in the positive x direction, and the direction of F1 will be this one, and direction of F2 will be this one at nodal point 2. Is it clear to all of you? Any
Yes,
doubt?
sir. No, sir.
Other people, please respond whether the problem is clear or not.
Clear, sir.
Fine. Okay. Okay. So these kind of problems you can expect. So if I want to say, what I can do is, if I want to increase the difficulty level of the problem, what I can do is, wait. Yes, if I want to increase the difficulty level of the problem, what I can do is I can add many elements. Here you can see that 3 elements are present. In the exam, I can give you a 5 element. Then in that case, the entire global stiffness matrix will be a 5 cross 5 matrix. You will get 5 different equations. You have to find out those 5 unknowns and so on. Only the difficulty level which one can make is that they may increase the number of element. Here in the in the class we are solving for a 3 element. Maybe in the exam you have to solve for a 5 element, you have to solve for a 6 element. Fine, but the procedure will be like this only if you are using the direct stiffness method. And remember one more thing, don't solve this problem by your normal strength of material approach. If you solve it, definitely you will get no marks, because this is not a strength of material subject, this is a finite element method subject. So you have to solve all these problems by the correct finite element method procedure. Fine, so this was the problem. Next, I don't think enough time is left. I won't be able to complete the next problem. But what I can do is that before complete solving that problem, let me give you some idea about that problem. We will be requiring those ideas. Already, I have given you those ideas in the very first module. Just to recap those ideas, that is this one. Yes, two things which you need to note for a one-dimensional bar element having uniform area of cross-section A and modulus of elasticity E over its entire length L, then how you can evaluate the element stiffness matrix. For example, if you consider this problem, you can see very clearly that this problem is divided into three elements. This is element 1, say this is element 2, this is element 3. This element 1 is present between node 1 and node 2. Element 2 is present between node 2 and node 3. Element 3 is present between node 3 and node 4. Assume that the length of the element 1 is say L1, length of the element 2 is L2, length of the element 3 is L3. Now if all the three elements are made up of same material, definitely modulus of elasticity that will be same for each material. If all the three elements are made up of different material, definitely the modulus of elasticity will be different. Similarly, modulus of rigidity is also different. So if I assume that all the elements are made up of same material, that means if E is same for all the material, then for a particular element, how the stiffness matrix changes? I know that stiffness matrix what? Stiffness matrix, that is Ke. Ke means stiffness matrix for a particular element. If I assume that this one is my that element, then I will write K of 1. K of 1 means stiffness matrix for first element. It will be how much? What is the size of the matrix? Size of the matrix will be equal to the number of nodes present. If I see this element 1 is comprises of only two nodes, that is 1 and 2. So the size of the stiffness matrix will be what? It will be a 2 cross 2 matrix. 2 cross 2 matrix. This will be, this row 1 corresponds to nodal point 1, row 2 corresponds to nodal point 2, column 1 corresponds to nodal point 1, column 2 corresponds to nodal point 2. So in between I have to write the stiffness matrix. I know it will be how much? K minus K minus K K. If the for this element number 1 stiffness is K. Fine. Now, if I take this K common, I can write K matrix 1 minus 1 minus 1 1. And this K is given by E into A by L. This I have made you derived in the very first module. If you see my third or the fourth lecture of very first module, you will see that I have there I have formulated this derivation. This K is how much? This is E into A by L. That means for this particular element number 1, E into A. What is the area of the element? Divided by L. L means for this element number 1, what is your length? Matrix 1 minus 1 minus 1 1. Now this Ke matrix, this element stiffness matrix, will be different for each and every element if other elements are having different length and different cross section and different material, if they are made up of different material. But if they are made up of same material, then definitely value of E will be same. So the stiffness matrix takes the shape like this, that is Ke For any element, stiffness matrix is given by EA by L in bracket 1 minus 1 minus 1 1. What is A? A is the area of the corresponding element. What is L? L is the length of the corresponding element. And what is E? E is the modulus of elasticity for the material of the element. Is it clear to all of you? Any doubts so far?
No, sir.
Okay, this we will be requiring in my next problem. So that's why I have told you before solving the problem. Similarly, if you want to say find out, if you want to find out how much stress is induced in each of the element due to application of nodal force at each and every, for example, if you see in this element number 1, at the second nodal point, a force of 100 kilo tensile force of 100 kilonewton is applied. Similarly, in element number 2, at the third nodal point, a compressive force of 40 kilonewton is applied. Due to these forces, what will happen? Each and every element will induce some stress, and that stress is given by, from the Hooke's law, I know that stress is directly proportional to strain. So stress is equal to some constant into strain, and that constant is what? That constant is nothing but modulus of elasticity, and is given by sigma is equal to E into strain. In matrix form, you can write sigma E. This sigma E is what? This sigma E is for an element. That means for this particular element, what is sigma? Sigma E is equal to E into epsilon matrix, that is strain matrix. And this strain matrix is given by epsilon is equal to B matrix into, that is the nodal displacement vector matrix for the element transpose of nodal displacement vector matrix for a particular element. And what is this B matrix? This B matrix is known as strain displacement matrix. This B matrix is known as strain displacement matrix. How this B matrix is coming, this you will learn in module number 4. So the derivation part is not at all associated with this particular module, so I am not going into that derivation part now. We will go into the derivation part when we will go for the fourth module. You just remember the final expression of this strain displacement matrix, and this strain displacement matrix is given by 1 upon Le. This is a matrix, and the size of the matrix is 1 cross 2 matrix. That means 1 row and 2 column, minus 1 of 1. So if you multiply this term inside, the final B matrix becomes minus 1 by Le and 1 by Le. That is first row and 2 column. And what is this Le? Le is nothing but the length of individual element. So then what you will do, you will substitute this strain displacement matrix over here. And what is this U? U is your nodal displacement vector of the corresponding element. If I consider this element number 1, I can say that nodal displacement at node 1 is U1 and displacement at node 2 is U2. Then I can write this nodal displacement matrix vector as, how I can write? I can write it as U1, U2, U1, U2, and this is what? This is your transpose. So if you take the transpose, this matrix becomes U1, U2. So you have to substitute this value for that particular element over here. For that particular element, you need to substitute the strain displacement matrix, multiply it with E, you will get the stress induced in each of the every element. Is it clear to all of you? Any doubt so far?
No, sir.
Fine. So this we will be doing it in our next problem, which is not possible today. So this we will discuss on the Thursday's class. So till then, goodbye. Fine. If anyone is still left to give his or her attendance, you may please write in the chat box, or else you can leave the meeting. Thank you.
Thank you, sir.
Welcome.